to make it reasonably efficient, and we haven't seen it as a bottleneck in any applications yet. So in each multiprocessor, there is 64K of constant memory, as the same as in the previous generation, and you can declare that with a special CUDA qualifier with the underscores constant, and it's cached read-only access, 4 bytes per warp per SM. But we added an additional feature which I think will eventually supersede the constant memory, and we call that uniform access. And it works through the normal cache system, and it uses that mode where data doesn't overwrite or pollute the cache. And so what you do is just use the C construct const, and as long as it truly is constant and it doesn't depend on a thread ID or something that can change between threads, it works effectively the same way as constant memory. And there's no limit on it. The advantage is you have infinite constant memory now, and guaranteed hit on the cache. Okay. All right. So I already talked. I'm going to talk now about the memory hierarchy, and I'll skip over the L1 cache part because we already talked about that. And you see it's kind of hard to talk about one part without the other, so I've already talked a little bit about the rest of these, but I'll fill in a little more. The L2 cache is a chip-wide resource. It's shared between the multiprocessors, and there's 768K bytes per GPU. And it's fully coherent across all of the multiprocessors and across the CPU. Every access to the physical RAM goes through L2, so it's guaranteed to be coherent. And that includes the mem copies from CPU to GPU and the other way. The GPU physical memory is 6 distinct partitions of GDDR5, and the memory interface is faster and wider than the previous generation. In addition, we support ECC now for HPC, and it's slightly slower with ECC because we use the same physical memory. So now a specific product, C2050, is the first Fermi that came out. There's 14 multiprocessors. We have about a gigahertz core clock and 1.5 gigahertz memory clock. You'll notice that these clock rates are significantly slower than CPU clock rates. Well, the core at least. The reason for this is that power consumption goes up super linearly with clock speed. So we want to have a power efficient implementation, and so we stay away from the bleeding edge of the clock rates. Instruction throughput, 500 giga instructions per second, and that enables over a teraflop of single precision with the multiply add instruction, and half a teraflop of double precision. And these are numbers that are pretty reachable with real code. You can actually get this kind of throughput with distinct data. So we could have pushed the peak number of FP32 higher, but not without increasing the memory bandwidth and the register bandwidth and everything else. And we haven't actually seen any applications where that is the limit. Memory bandwidth is higher than the previous generation, and we've kind of trying to be on a path of a factor of 2 every 18 months with that. For the on-chip bandwidth, we can't do that, of course, with the external, because the DRAM technology doesn't permit it. So a good balance of computation to memory is about between 3 and 4 to 1 instruction to memory access. And if you're higher than that, your program is instruction bound. If you're lower than that, you're memory bound, because you can't feed enough operands to keep yourself busy. And that ratio changes with ECC because it changes the effective memory bandwidth. So all of that so far is pretty much same functionality as before, but bigger, better, faster, more easier to use, and better throughput. There's also some new features that we've added from the compute point of view. And one of those is the ability to execute multiple kernels concurrently. So the thread blocks from the first kernel are launched first, and if there's still resources and space in the machine, thread blocks from another kernel in another stream can be launched. So what that gives you is you could build an application that has 2 different kernels that are linked together with producer-consumer sort of way, and they communicate through queues in global memory with atomic operations, as long as you are sure that all the blocks will be launched. We've also added and improved the copy engine architecture. So we have 2 distinct copy engines. So you can now copy simultaneously from CPU to the GPU your input value, and from GPU back to the CPU your output values. So if you triple buffer your data in your application, you can be copying data, executing the previous set of data, and copying back the results from 2 sets ago. And previous generation could only do 1 copy at a time and not completely overlap asynchronously. So this is potentially a factor of 3 speed up for something where your application is balanced with data traffic and computation. And ECC covers all the on-chip memory as well as the external DRAM, so full ECC implementation. So the programming model is largely the same as previous generations. The biggest difference, which I mentioned earlier, is the memory is accessed in groups of 32 threads, which matches the warp thread width. And really, that doesn't affect you except for efficiency if you are aligned 32 wide, and if you are reading data in multiples of 32, then you'll see a good speed up. And again, this is something that is only going to get bigger. The alignment constraints are going to get larger as the memory granularity gets larger. So it's just a good habit to get into, to always try and keep everything blocked and aligned as much as you can. So this is what I commented on earlier about the L1 and the L2 cache. Is it's really not designed to provide reuse like you see on a CPU. So you don't think about building your program blocking for the cache size. If you actually know how to block the data for access for your program, you should use shared memory for that. If you know how to manage it, you should manage it, because you're going to do a better job than any cache system. Really, all the cache is doing effectively is when you have misaligned accesses that are going to have reuse on the order of a few cycles later, you read your multiple chunks from memory that are misaligned, and then the next cycle you're going to read the next misaligned piece, and you can reuse the half of the piece that you didn't use the last time. Small strides will get a good multiple. And register spilling. In the original G80, the memory space that we called local memory is where operands go if you run out of register space. And it was called local because it was private, but it's not local as in it's nearby. Local memory was actually going all the way to global memory, no cache. So what we get now with the L1 is you can spill to L1 if you run out of registers, and so that's quite helpful. It's quite a bit faster. So things that you can do, you can decide, experiment with more or less shared memory in L1 cache, and you can also experiment with this this granularity where you don't pollute the cache when you're doing accesses. So that's it for the hardware. I'm going to talk about a handful of software tools and features that we've added. And then at the end, I'll speculate a little bit on the future. How are we doing for time? Okay. All right, great. Okay, so I'm a hardware architect. I'm gonna talk about the software like a tourist because it's not my area. So we started out with CUDA C, which was a subset of C with some additional features for parallelism, and we've been gradually improving that. We're now adding a lot of C++ features, and we're very close to full C++ compliance. We also have support for Fortran, OpenCL, and Microsoft's Direct Compute. Really, the way we think of our ecosystem is we build a parallel multiprocessor on which any language can be implemented as long as it contemplates parallelism. So we've started building this ecosystem, and we're trying to keep as many pieces as we can open source so other people can build pieces and contribute. We've also built a handful of tools on top of the compiler level to try and make it easier for people to develop. Debuggers, profilers, and we work with several development environments, and we provide libraries for basic functions. So when we say CUDA, we mean the green thing on the bottom.
Has a question.
Oh, yes?
Be any compliance or any with C#?
Could you ask that again? It didn't quite come through.
Yeah, you're cutting in and out. Can you try again?
Yeah, is there any planned compliance with C#?
I think you'd have to ask Microsoft. I think the hardware is capable, but someone would need to develop the tools. And I don't think that it's our intent to populate this language space. We provide the basic building blocks so other people can build on top of it, and then we try to work with partners to enable them to do it. So I would like to see Microsoft do a C# implementation on top of the CUDA architecture. I don't think we'll do it. We started with CUDA C and have been gradually extending that to C++. We have over 60,000, actually that number is close to 100,000 now, active developers, and we measure that by people who are actually active with downloading and re-downloading our SDK. And now the SDK includes a whole bunch of other things beyond the compiler. We maintain leadership implementation of OpenCL. We're, I believe, the only fully compliant GPU implementation, but I'm hoping to see another one soon. We're releasing new versions of OpenCL every time there's a new spec release, usually on the same day. So we're very active in that. We're fully active with Direct Compute, which is Microsoft's compute API. We've worked with partners to implement parallel Fortran on CUDA, and numerous external people are building other interfaces to run programs on the GPU. You can find a lot of these on CUDA Zone at NVIDIA.